In this section, we're going to look at solutions. And here on the screen, we have an example of coffee as a solution. So coffee is a complex mixture with many solutes. It has some different large organic acids, has caffeine, it has many other flavorings and stuff like this. And in this case, this person is adding another solute, sugar, which is being dissolved into the coffee. But it only has a single solvent, which is water. So water, or the solvent in general, is the part of the solution that maintains its physical properties the most. Or it's the part that's in the most concentration in most cases, in the greatest amount. So let's look at an example. If you take salt, which is a white powder, and you dissolve it in water, which is a clear liquid, you make salt water. Salt water is also a clear liquid. Salt water looks a heck of a lot like water. So therefore, salt water is the in salt water, water is the solvent and salt is the solute because the salt loses its physical properties. Salt water is not a white powder. So that's basically how it works. It's also true that there's more water present than there is salt. On occasion, you could dissolve more of a solute in a solvent, where there's actually more solute present than there is solvent, but that's fairly rare. The solute is the thing that dissolves into the solvent. Note that you can have many solutes. So in this case, you only have one solvent, in case of coffee, water, but you have lots of solutes. Some qualitative terms we can use for solutions are concentrated and dilute. And if you look here, a person has a more concentrated sample of probably blue food coloring, and then they add water, and the concentration gets more dilute. So if you want to dilute a concentrated solution, you can simply add more solvent. So here, blue food coloring is the solute, water is the solvent. And if you want to make it more dilute, you add more water, more of the solvent. So adding solvent dilutes things. But these are qualitative terms, meaning they don't have numbers associated with them. And as you can imagine, in chemistry, we want to know the actual concentration of this solution. We don't want to just know that this is more concentrated than this. We want to know the actual concentration of this, or potentially the actual concentration of this. And what we're going to look at mostly in this section is how to calculate those concentrations, and then how to use those concentrations to find other things once you have the concentration. So in this course, the unit of concentration that we use the most, although not exclusively, is molarity. And molarity is defined as moles of solute divided by liters of solution. So a couple things to note here. First of all, the amount of solute, the thing that's dissolved, needs to be in moles. If it's given in grams, you need to convert it to moles. So that's basically that. And the other thing to note is it's liters of solution. So it's the total volume of the solution in liters. So that's also important to note. One thing that's going to come up a lot when you're calculating molarity is converting milliliters to liters. For practical reasons, like in the lab, in a chemistry lab, we don't usually use liters of solution for the scale of the reactions that we're doing. We usually use milliliters of solution. So we need to be able to quickly convert from milliliters to liters. Remember that 1 liter equals 1,000 milliliters. And given here are several examples. 225 milliliters is 0.225 liters. Skipping down, 25.4 milliliters divided by 1,000 is 0.0254 liters. 8.27 milliliters is 0.00827 liters. Notice that I'm moving the decimal place 3 times in each case, so it's here 1, 2, 3, and you get this. It's here 1, 2, 3, and you get a leading 0, and you get this. So I'm just moving the decimal place 3 times, or I'm dividing by 1,000. This is something you're going to have to do a lot, so it's important to practice converting milliliters to liters until you're comfortable just doing it in your head. So now what I want to do is, like in several other sections, I want to go through several examples of molarity calculations, and these examples are typed out for you on the slides, but I don't feel that this is going to do much justice if I just go over it on the slide. So instead, I want to go over it on a piece of paper, and I think it would be a good idea if you took notes as we went through this. So in this first example, we're going to calculate molarity. So in this case, we're going to take 22.8 grams of NaCl dissolved to make 500 mLs of solution. And we want to know what is the molarity of this resulting solution that you make when you take 22.8 grams of NaCl and dissolve to make it 500 milliliters of solution. Now, we can make this look like dimensional analysis, but it is not exactly dimensional analysis. Remember that in dimensional analysis, we're converting from one unit to another, and the quantities are equal. In this case, we won't be exactly doing that, even though it'll look the same. So let's look at how we could do that. Well, in order to find molarity, which you'll recall, molarity is equal to moles of solute divided by liters of solution. We could convert this grams to moles, plug in, convert this milliliters to liters, and plug in. I should make clear that this is 500.0 milliliters of solution, so we have the sig figs correct. Or we could do this by something that looks like dimensional analysis. So again, we could convert from grams to moles and plug in, we could convert from milliliters to liters and plug in, and we could solve it that way. And that's perfectly a reasonable thing to do. But I'm going to do something that looks a little bit more like dimensional analysis because, one, we learned how to do dimensional analysis, and this just gives us more practice. So what I want to do here is take grams of NaCl and convert it to moles of NaCl. This is dimensional analysis. But the next part is not. I then want to take those moles and divide by the volume of the solution in liters. So I want to divide by the liters. This is technically not dimensional analysis because I'm creating a new unit. I'm not just changing the units. So what I want to do here is I need an equality between grams of NaCl and moles of NaCl. Well, if we look at our periodic table, the molar mass of NaCl is 22.99 plus 35.45, which is 58.44 grams per mole. So what we know is that 1 mole of NaCl equals 58.44 grams of NaCl, which we find from the periodic table. The other thing we need to know is that our volume in liters is 0.5000 liters. So starting with, move this up a little bit, 22.8 grams of NaCl times, well, we want grams to cancel out, so we're going to put that on the bottom, 58.44 grams of NaCl on the bottom, and on top, 1 mole of NaCl times. Now, if you want to divide using something that looks like dimensional analysis, you put a unitless 1 on the top. Then on the bottom, you put the volume in liters, 0.5000 liters. Multiply by the top, divide by the bottom, multiply by the top, divide by the bottom. When you do all that math, your calculator will tell you 0.780287 and some more numbers, which we need 3 sig figs. Since this is 3, this is 4, this is 4, we need 3. So this is 0.780 molar NaCl solution. Now a minute ago I said that if you want to divide in dimensional analysis, you want to take 1 over the number for multiplication. Let me just show you that in a practical example. Let's say we have the number 8 and we want to divide it by 2. If you take 8 divided by 2, you get 4. Well, if you can only multiply, because in dimensional analysis you are forced to multiply, what would you want to multiply 8 by to get 4? Well, if you take 8 times 1 over 2, just like we took 1 over 1 over 0.5000, if we take 8 times 1 over 2, it's the same as 8 divided by 2, and we again get 4. So that's where this comes from. It looks like dimensional analysis, but it's technically not. So what I do in my notes is this arrow means convert units. This, if it's a multiply or a divide, it's usually divide. It means change the units. Now that we've seen how to calculate the molarity, let's look at an example of how we can use molarity to calculate something else. And this is very important and very common in chemistry. So we need to be able to do it. So in chemistry so far, if we wanted to convert to moles, we would take grams and a molar mass and convert it to moles. It turns out that when we have molarities, we can use a volume and a molarity to find moles. And in fact, these are the two ways in chemistry we have to find moles. There are others, and you'll actually learn some others, but up until this portion of the course, and for the first part of this class, including the first exams, you're only going to have two things that you're going to be able to convert to moles. And those are grams, using a molar mass and a periodic table, and molarity, using a volume and a molarity, you can find moles. So here what I want to look at is, how do you use molarity as an equality? Well, molarity is an equality because it relates to units. It's moles per liter. Like way back when we did the dimensional analysis, where a person was making $12.75 per hour, 1 hour equaled $12.75. Well, a molarity is moles per liter. So if you have a 0.875 molar HCl solution, the equality is 0.875 moles of HCl, the molarity of number of moles, equals 1 liter of solution. If it's 1.87 molar, it's 1.87 moles of MgCl2, and I notice that's not subscripted, equals 1 liter of solution. If it's 6.2 molar, it means 6.2 moles of NaOH equals 1 liter of the solution. So notice, it's always the molarity number of moles, 0.875, 1.87, and 6.2. These numbers all match, and it's always equal to 1 liter of solution. So using molarity as an equality is extremely important in this class. So it's something we need to be able to do. So now let's look at a few examples where we have to use molarity as an equality to solve something else. So for example, we could be asked, how many moles of NaOH are in 700.0 milliliters of a 3.00 molar NaOH solution. So we want to know how many moles of NaOH are in 700 milliliters of a 3 molar solution. Well, here our plan of attack is liters of NaOH to moles of NaOH. And if you recall a few minutes ago, I said you're going to have to get used to converting milliliters to liters, because often we're given the volume in milliliters, in this case 700. It's kind of hard to see, but 700 milliliters, we have to convert that to liters. So we're going to start with liters of NaOH, and we're going to convert it to moles of NaOH. Well, if we want to convert from liters to moles, we need an equality. Well, how do we write that equality? It's the molarity number of moles, 3.00 moles of NaOH, equals 1 liter of the NaOH solution. And I usually write it as subscripted NaOH, but you can write it however you want. So it's 1 liter of this solution. So this is basically what we have. Remember, we're starting with the volume in liters, not milliliters. We divide by 1,000 or move the decimal place 3 times. And we get 0.7000 liters of, in this case, NaOH times, what do we want on the bottom? Well, we want liters of NaOH to cancel out. So we put the 1 liter of the NaOH on the bottom. And on top, we put the other thing, the 3 moles of NaOH. And when we do this math and round to 3 sig figs, what we find is that we get 2.10 moles of NaOH in 700 milliliters of a 3 molar solution. So to convert from liters to moles, we need an equality. This equality comes from the molarity. 3 molar means 3 moles of NaOH equals 1 liter of solution. Note that the number of moles is always the same as the molarity, and this is always 1 liter. The last thing to point out, and I said it before, but I want to say it again, you do need to use your volumes in liters. So make sure you're converting your milliliters to liters. If you plug in milliliters here, you will unfortunately get an incorrect answer. So that's just one example. Let's look at another example where maybe we could go a step further. This one is how many grams of NaCl are required to make 250 milliliters of a 1.50 molar NaCl solution. So this is a step further than the previous example. So in this case, we need a plan of attack. So in this case, we know how many liters of NaCl we have, and that's actually what we're starting with. So we're starting with liters of this NaCl solution. We can convert that using the molarity to moles of NaCl. And then, of course, using the molar mass, we can convert from moles of NaCl to grams of NaCl. So in this case, it's an example where we're converting liters to moles. In order to convert liters to moles, you need a molarity, because a molarity relates liters and moles. So that's how we can do this. So here, the liters of NaCl to moles of NaCl, we know that 1.50 moles of NaCl is equal to exactly 1 liter of the NaCl solution. It's always, again, the molarity number of moles equals 1 liter, always 1 liter. For moles of NaCl to grams of NaCl, we use the periodic table. So Na is, if we can see it here, 22.99. Cl is 35.45. So 1 mole of NaCl equals 22.99 plus 35.45, which is 58.44 grams of NaCl. Remember, we need liters of NaCl. You've got to get used to converting the milliliters to liters, as I've said a few times. So we're going to take 0.2500 liters of NaCl. Remember, you simply move the decimal place 3 times or divide by 1,000. Times, now we need to go from liters to moles. Well, what do we want on the bottom? In this case, we want the 1 liter of NaCl on the bottom because we want liters of NaCl to cancel out. On top, we want 1.50 moles of NaCl times. For the last one, we're going from moles to grams. Well, we want moles to cancel out. So we put the 1 mole of NaCl on the bottom, and on top, we put the 58.44 grams of NaCl. Multiply by the top, divide by the bottom, multiply by the top, divide by the bottom. This molarity has 3 sig figs, so our answer should have 3 sig figs, and it turns out that it's 21.9 grams of NaCl. So this is using molarity in a calculation. When we get to stoichiometry in the next chapter, we'll use molarities to calculate stoichiometries, to calculate moles for stoichiometry. So it's very important to get practice doing this. I want to go through one last example of these types of problems, and then I want to talk about dilution. So here, in this last example, it says how many moles of chloride are in 750 milliliters of a 1.20 molar magnesium chloride, which is MgCl2 solution. How many moles of chloride are in 750 milliliters of a 1.2 molar MgCl2 solution? So, this is an interesting question. And it turns out that if you take MgCl2 solid and you dissolve it in water, it forms Mg2 plus aqueous, its stable ion, plus Cl minus aqueous, the stable ion. And since there are, this is MgCl2, you're actually going to get 2 Cl minuses. So when ionic compounds dissolve in water, they're breaking up into their stable ions. And in a minute, I'll go through a couple more examples of this after I complete this problem. So this is important because for every one of these, we have two of these. So let's look at our plan of attack. In this case, we're starting with an amount of magnesium chloride solution. So we're starting with liters of MgCl2. We're going to convert that to moles of MgCl2, and then finally to moles of Cl minus, because it asks for how many moles of chloride, which is just Cl minus. So to go from liters to moles, we use the molarity, of course. So it's 1.20 moles of MgCl2 equals 1 liter of this MgCl2 solution. Now, moles of MgCl2 to moles of Cl minus is a bit different. So we have, in this case, 2 moles of Cl minus for every mole of MgCl2 because it's MgCl2. So 1 mole of MgCl2 provides or is equal to 2 moles of Cl minus in solution. Now, starting by converting our volume to liters, divide by 1,000, 0.7500 liters of the MgCl2 solution times. Well, what do we want on the bottom? Do we want the 1 mole or the 1.2 moles or the 1 liter? Well, we want liters to cancel out, so we put the 1 liter of MgCl2 on the bottom. On top, we put 1.20 moles of MgCl2 times. Now the relationship is 1 MgCl2 gives us 2 Cl minus. So we put 1 mole of MgCl2 on the bottom, because we want MgCl2 to cancel out, 2 moles of Cl minus on the top. I should note that this and this are measurements. These are exact numbers. These are counted. There's exactly 2 Cls in 1 MgCl2. So we don't use that in sig figs. So this is 4 sig figs, this is 3 sig figs. Our answer should be 3 significant figures, which is 1.80 moles of Cl minus. So when some ionic compounds dissolve in water, okay, the ones that are soluble in water, they break up into ions. So if they'll dissolve, they break up into ions. So if we were to take, for example, NaCl, solid, and dissolve it in water, it would break up into Na plus, remember, sodium is +1, which is aqueous, dissolved in water, plus Cl minus, aqueous, which is dissolved in water. Remember that Cl minus is a stable ion because it's in 7A, and A plus is a stable ion because it's in 1A. Let's look at another example. Let's look at CaCl2, solid. This is calcium chloride. So in this case, the stable ion, calcium's in 2A, is Ca2 plus, aqueous. And when it forms solution, it still has Cl minus in it, plus Cl minus, aqueous. But because there's 2 chlorines here, we have 2 chlorines here. So these are how the ions are breaking up in solution. Let's just look at one last example. What if we were to take table sugar, C12H22O11, solid, and dissolve it in water? Sugar certainly dissolves in water. It stays as C12H22O11, aqueous. It doesn't break up. And you might ask, well, how do you know these break up and this one doesn't? Ionic compounds break up in water to form the stable ions, but covalent compounds, like sugar, which does not contain a metal, so therefore is covalent, do not break up in water. So therefore, they just become aqueous if they dissolve in water. This is not to say that everything dissolves in water, but if it does dissolve, ionic compounds do this, and covalent compounds do this. And we'll talk about this more later in the course. I just thought it was a good opportunity to give an introduction to this material. So the last thing that we want to look at in this section is diluting a solution. And as we talked about a few minutes ago, diluting a solution involves adding more water. So if you have this concentrated blue food coloring solution and you want to make this dilute one, you simply pour water in. So you can, that will change the concentration by adding solvent. However, that's only qualitative, right? We need a quantitative way to deal with this. And the quantitative way to deal with this is the equation C1V1 equals C2V2, where C1 is the initial concentration, C2 is the final concentration, yes, C2 is the final concentration, so initial concentration, initial volume, final volume. In a dilution, we're simply adding more solvent. So if we take a concentration times a volume, if that concentration is molarity times a volume, we get moles. If we take then the final concentration times the volume, we get moles. And if we look at this up here, the amount of blue food coloring is unchanged. There's the same number of moles of blue food coloring in this flask as in this one after. So if this is like before and after, the number of moles of blue food coloring are the same. The reason this one's more dilute is because we added more water. The reason that I'm pointing this out is because the dilution equation can only be used if you're doing a dilution. It's only mathematically valid if the amount of solute on this side and the amount of solute on this side have not changed. If the amount of solute changed, if you mix two solutions that both contain blue food coloring, you cannot use this equation because you are not simply changing the volume of the solution or the amount of solvent. So now let's look at a couple examples of how one can use practically the dilution equation. And again, I'm going to switch back over to the lecture notes. So it says how much 2.00 molar HCl is required to make 500 milliliters, I should put it over here, milliliters of a 0.100 molar solution. So how much 2 molar HCl is required to make 500 milliliters of a 0.1 molar solution? Well, this is a dilution. So we're starting with some amount of this 2.00 molar solution, and we're going to add water such that the total volume of the solution is 500 and the final concentration is 0.1 molar. So let's look at the equation. Well, the equation is C1V1 equals C2V2. Because we're doing a dilution, we can use this equation. The initial concentration, which is the higher concentration, is 2.00 molar. The initial volume is what we're trying to find out. How much of this 2 molar solution is required is what it asks. So V1, I'm just going to leave it as V1 as the variable. The final concentration we're trying to make is 0.100 molar, and the amount we're trying to make is 500 milliliters. This is one case where you actually don't have to convert this to liters. It would not be wrong to convert it, so if in doubt, convert. In the previous examples, if you didn't convert to liters, you'd get the wrong answer. But here you don't have to convert to liters. So I'm going to put it in as 500 milliliters. We multiply these two and then divide by the number next to the variable. So multiply the two numbers and divide by the number next to the variable, and we find that V1 equals 25.0 milliliters. So what does this mean? It means we need to take 25.0 milliliters of 2.00 molar HCl and add 475 mLs of water. You may ask, well, why 475 milliliters of water? Well, the total volume of the solution has to be 500 milliliters. So we need 25 milliliters of this solution, and the rest, 500 minus 25, or 475 milliliters of water. On a test, you probably won't be asked for this last sentence. However, in the lab, if you actually need to make a solution like this, and you will need to make many if you take the lab here, then you do need to know this information, because you do need to know that you take 25 milliliters and add 475 milliliters of water. Let's do one more example here, and then we'll finish up with this material. So it says, what is the concentration of the solution when 20.0 milliliters of 1.25 molar NaCl solution is diluted to 250 milliliters. All right, so this dilution question actually has the word diluted right in it. They don't all, but this one does. It says, what is the concentration of the solution when 20 milliliters of 1.25 molar NaCl solution is diluted to 250 milliliters? So of course we're going to use C1V1 equals C2V2 in order to figure out this final concentration. Here we know the initial concentration. It's 1.25 molar. We know the initial volume, and again you can plug the volume in milliliters. It's 20 milliliters. We're taking 20 milliliters of this 1.25 molar solution. The C2 is the variable. The first few words are, what is the concentration? Well, what is the concentration when you do this dilution? We don't know. We got to figure that out. And then the final volume is, we're going to dilute it to 250 milliliters. And again, you can plug in milliliters for the volumes. Multiply the two numbers together and then divide by the number next to the variable. So 1.25 times 20 divided by 250, and you will find that C2 equals 0.9000 molar. So this is the final concentration of the solution after you do the dilution from 20 milliliters to 250 milliliters. So in this section we covered molarity and what molarity is and how molarity can be used to find moles. This information is extremely important for the next chapter. It's very important to practice with this.